principal scientist at Adobe, which means that I'm basically a director level engineering position, where I get to spend part of my time doing research and development to solve different security problems. And so in this presentation, I'm going to show you some of the latest stuff I've been working on to try to help Adobe secure our services in the cloud. So we can go ahead and just jump right into it. Like you, I went to a California State University school at San Diego State Aztec. And when I graduated from school, most of the applications sort of looked like this. They're fairly simplistic in design. A lot of them were monolithic. And so the person came across the internet. They would talk to the web servers. If the company was a little bit more advanced, they had the web servers separated from the app servers. And then I talked to a database. And so it was pretty simple. You know, a linear flow of data from beginning to end. And if you wanted to secure the applications, there were a limited number of entries. But towards the late 2000s, beginning of the 2010s, things started to move towards microservices. You had microservices-based approach. So if you were in the Kubernetes workshop that preceded this, Kubernetes is definitely part of deploying microservices.
Do you want to just maybe use few sentences to describe the difference between the microservices and container?
Okay, so the container is basically about how you host it,
Right.
and a microservice is more of a philosophy of design of how you build the application. And so in a monolithic application, you would have one web server and it would be responsible for the entire website.
Right.
And so a lot of small companies, they have monolithic applications because their websites aren't that complicated. So the website's responsible for anything that goes on the website, like collecting form data, logging the user in, interacting with whatever data that the website stored. In microservice architecture, each application has a single purpose. And so you write much smaller applications which do one and one thing only. And so in this diagram, you have one microservice which is represented for a web UI. This is just an example one. You have one which is driver management. You have another completely separate web service which is just payments. And these things are separated on the network. They're individual instances that are on the host. Each one has its own specific. Sometimes they are full web servers, so they might be running on Nginx, which is what they're showing here. Sometimes they can be Lambda functions, which means that they are it's running a platform called Functions as a Service, where it's just
function as a service. Okay.
Yeah.
So on the container, we know that container is kind of part of Docker, part of the Kubernetes. But
Right.
here, microservices, do they have some kind of thing that wrap?
No, each microservice is written in its own stack. So Kubernetes would be one level underneath this. So Kubernetes lets you run a large number of services that are very small. And if you're writing really small services, chances are you're shoving them into Docker containers, and then you're running those Docker containers.
So you can use Kubernetes to manage all the microservices?
The infrastructure underneath. Yeah,
Got it.
where all these things have to have a Linux host environment in order to run. So you can make it simple. If you're using functions as a service, even more of it's being managed by the cloud provider. But yeah, it gets a little bit different. But basically, the idea behind a microservice is rather than having one big monolithic application which does everything, you break it up into tiny little microservices, each which do their own thing. And that can get pretty complicated. So this is Netflix. I believe these images are circa 2004. I might be slightly off on the date. But Netflix is, according to the last stat I saw, run by over 700 different microservices. 700. Which is how you get this planet-like network diagram over here. There's a lot of stuff that's going on when you log into Netflix. They have to figure out who you are. What movies did you watch last? Or what movies did everybody you're sharing your account with watch last? What new movies are there to promote? It gets, and to track data flow in this, like if you're trying to track sensitive data through a network like this, it gets complicated because there's no one single path. One service can talk to multiple other services, and you can lose insight to where things are going and how things are routing. And Amazon was also a big push for that. So this is Amazon's diagram. And Amazon provides a lot of the infrastructure that microservices people use. EKS is their Kubernetes infrastructure. That's the symbol for Lambda, which is their functions as a service. And if you think about it, if you go shopping in Amazon, a lot of stuff happens when you hit the homepage, just by hitting the homepage. It first checks to figure out whether you're logged in. It checks to figure out, what level are you logged in at? Like, does it just know who you are, or have you already been authorized to like go change your payment gateways and things like that? Once it knows who you are, it has to go figure out what you purchased last. So, hey, you bought a bike, maybe you want to buy a helmet. They have to figure out what they're promoting that week so that they can show whatever the key items for that week are and put that in front of you. They have to start a session to track everything you're going to do in this shopping session so that the next time you come back, they can learn from what you did this time and tell you again when that comes back. There's just simple things like returning the HTML page to you, and getting just the core framework of the website to you. So their microservices get really complex. And they have what's known as a two-pizza rule. And what that rule is if any team can't be fed by 2 pizzas, if it requires more than 2 pizzas to feed the team's too large. You should probably break them up and split up what they're working on. And so that can make things more complicated because now you have tons and tons of different teams, and there's no single place you can go to find out the information. If you work for a small company and you want to find out about the network, and you have one network admin, everything's really easy. You go ask Bob. Bob tells you. You go back to your desk. He probably sits next to you. If you're working in an environment like this, it could take you several questions just to figure out which team manages that and figure out what each team does to secure their infrastructure along the way. So these things can make life complicated. And so security had to adapt. As the world got more complicated, we had to adapt. And one of the people who was looking at these problems, his name's John Lambert. He works at Microsoft. Very bright guy, good guy to follow online if you're interested in security. And he wrote a blog, which a lot of people quote, which is, defenders think in lists, attackers think in graphs. As long as this is true, attackers win. And what he means by that is, as a defender, I have all sorts of things I have to go through every day to make sure I keep my environment secure. Are the passwords rotated? Are the machines patched? Have I audited the firewall rules recently? Am I keeping up with all my compliance stuff? When was the last time we reviewed something? I have to go do the threat models. There's just a punch card of all these different things you have to go through in order to keep your environment secure. But when you're an attacker, you don't think like that. Attackers often come at things with black boxes, and they don't have any preconsumptions or preconditions that define how they're going to go about attacking your network. They just start at one place, and they see where things take them, and they move a little bit, and they learn a little bit, and they move a little bit more, and they attack a little bit more. And when attackers are attacking complex environments, they often don't get roots in the core customer database right off the bat, right? They go and they compromise a less important system, and they hang out there for a little bit, and they try to find their way all the way back to where the crown jewels are, which is usually buried farther back in the application stack. So they have to kind of meander their way around. And they may have like some lists of things they go through based on their personal preference on how they attack things, but it's all very exploratory for them. And that gives them an advantage because they don't have to go through lists and lists of stuff every day. They just go through what they have to do. And this idea got perpetuated in other blogs. You've got the dangers of linear thinking and why security analysts should defend in graphs from Rapid7. If you go to Amanda Rousseau handles the Facebook Red Team. And the banner that she has on her Twitter profile, at least at the time that I took the snapshot, was from their Red Team. And it says, Red Team hack the graph. And for Facebook, they obviously have to think in graphs because they manage a social network. A social network is, if nothing else, a graph of connections. But again, you can kind of see this idea being perpetuated within the security community. And then a bunch of security research came out of it. People started applying the idea of using graphs for everything from fraud detection to insider threat detection to penetration testing to spam detection. It was something that really got sort of perpetuated as a way of analyzing things and and coming at problems from a different perspective. So in the case of spam detection, some spam detection is based on grepping the message and looking for references to Nigerian princes or malicious URLs and a whole bunch of things based on the body of the message. But if you're thinking in terms of graphs, you could look at something more simplistic, like, has this person ever emailed this other person before? Is there anything that actually connects these two? Do they work for the same company? And you don't have to worry about what's in the body of the message. You can just look at how things relate, and that gives you some information. And so people who do forensics start using graphs. So this is an open source tool called Grapple by a hacker known as SandyBit, and he goes and he maps processes and what processes launch other processes, and that can be a way to go look for attacks in an operating system, because if you see Microsoft Word launching a shell, or if you see a web browser launching a shell as a child process, that might be a sign that an attack's occurring, because on an average day, Chrome isn't launching a shell, or at least it shouldn't be if things are going well. But if you can see in a graph that this process launched that, then you've got information. Another tool that's based on graph theory is Bloodhound. And this goes back to what I had mentioned with John Lambert, what he looks at. And let's say the person at the top is a very privileged system administrator, and this person down here is working in tech support. And you land compromise in the tech support person's box. You get them to click on something, through social engineering by calling up and saying you're having a problem and getting them to click on something. What's the graph for him to get to that person's credential? What machines would they have to compromise? What do these people have in common, and how do I get there? So if you start to put these things out in graphs, you can start understanding things. And graphs also help break down preconceptions that you have about how they might go about doing it. Because a lot of times as a defender, you get locked in your mind like, oh, well, they're obviously going to take this obvious direct route to get to that credential. And there may be a whole bunch of other paths that also exist that you're not thinking about. And so if you start visualizing them in graphs, you start to get there.
The graph is a concept. It's not a tool, right? Just
well, I'm going to get into, so I'm talking about graphs as a concept.
Okay.
There are graph databases, which I'm going to get into, and that's an actual implementation.
And that will allow you to see the data flow?
Yeah. In other talks, I mentioned tools like Maltego, which there's a free version of Kali Linux. It helps you graph networks. But yeah, at this point in the talk, I'm talking mostly about the concept of a graph. But to circle back around to what John Lambert was talking about in his original blog, he said defenders should take a lesson from how attackers come to understand the graph. Attackers study the infrastructure as it is, not as an inaccurate mental model viewed from an incomplete asset inventory system or a dated network diagram. Manage from reality, because that's the prepared defender's mindset. And so when you work in defense, you'll see a lot of vendors, they'll use a phrase called shift left. And the phrase shift left comes from the idea of the traditional software development lifecycle, where you have design, development, testing, rolling out to production, and then maintenance. And the goal with the shift left philosophy is you take your security resources and you try to get them involved earlier in the process, which would be left on the flow of how software is developed. And there's a lot of value in that. If you put more security in things into the design phase, you can prevent problems which will manifest themselves later on. And so it's the ounce of prevention prevents a pound of cure philosophy. But there are problems associated with that. Everything has its drawbacks. And the drawback is when you invest heavily on the design model, a lot can happen between when something's prototyped and when it actually makes it to production. Design is theory. Production is reality, right? So as you're creating the application, you're going through things, stuff will change. And what you threat modeled at the beginning may not be exactly this thing that ships at the end. And that can create gaps. Or as the thing gets maintained over time, things will fall behind in terms of maintenance, and that creates gaps. And so if you are measuring things as they are in reality, if you're actually going out there and measuring and creating graphs of what's actually deployed, you're working from reality. You're working from what's actually out there, not from what the paperwork says is deployed or what you think is out there. You're working from what you're actually seeing in the network. So if this is so great, what prevents graph-based approaches? And there can be, if you're working in a large organization, there can be a lot of things which prevent you from taking a graph-based approach. Your company is probably broken up into silos if you're a large enough company. There can be disjointed technical approaches. At Adobe, where I work, we're deployed in Google Cloud Compute and Azure and AWS. So there's no one cloud provider that has a complete picture of our network. We also have our own IT data centers, which run stuff. So for me, there's no single place I can go to solve that. And so what ends up happening is, you're getting a degree in computer science. So you think, science, okay, this is everybody in lab coats working in a pristine environment where everybody's got gloves and face masks. And I've got my hypothesis, and I'll do my materials and methods, and I'll do my experimentation, and I'll get a clean conclusion. And what I do is science. And there's a lot of science involved in what we do, but there's also a lot of craftsmanship when you have to deal with real world situations. So for instance, my parents love to do home improvement. They have never not been working on their house doing something. And if you've ever done home improvement, you learn the differences between reality and implementation. You want to go change your kitchen countertop. And the original kitchen countertop's a bunch of small little tiles, and you're like, I want to change it to a granite slab countertop because that's the new hotness in homes. So you go and you pull up all the tiles, and you go and you lay down the new granite slab countertop, and it kind of goes like this. And it's because your kitchen counter was never actually level when they installed it. And when they had tiles, they could adjust for that because small little tiles can deal with the flow of something not being level, but a solid granite slab's not going to do that. So then you have to go and deal with reality of the fact that it's not square. Or you go get a new door, and the door frame's not square. You start to deal with these sort of real situations. So sometimes you're dealing with, as computer science, as a computer craftsman. But that's not always a bad thing. There's a lot of things in computer science where fuzzy math is okay. So if you deal in binary exploitation, you'll hear phrases like heap sprays and NOP sleds. And that's because if I can cause a computer to crash, that's cool. That's a sign I can get to exploit. But I may not be able to predict exactly where it's going to jump to when it crashes. And so I just go and I spray all of memory with my code and hope that the mathematically works out that when it does do the jump, it jumps into one of the areas that I controlled, and I'm able to take control of the flow of the application from there. If you do fuzzing of binary applications, there's a lot of studies that prove random fuzzing with a good corpus as a baseline will actually outperform fuzzing which is tailored to that particular file format. There are some caveats, but it's sort of a general rule. Sandboxing assumes that you can't secure every line of code, so you take an approach that says, okay, I'm going to lose this battle, I'll try to win on a different front. And if you go into machine learning is all about something that's 98% correct or 99% correct. So no machine learning algorithm is ever 100% correct, because if it could be, they wouldn't need machine learning. They would write a direct algorithm. In machine learning, you're trying to balance your true positive rate against your false positive rate in a technique called area under the curve. And you're trying to figure out how to get as close as you can to 100%, but you're never actually there. And so when I started learning about machine learning, it was a good exercise for me because it got my mind out of the assumption that if I can't do something perfectly with a computer, I just shouldn't do it. Because computer science is based on math. Math, 1 + 1 always equals 2, and it's very clear, linear. It's always going to come out. But there's a lot of places in math, or in computer science, where close enough actually does get you where you want to go. And all of your self-driving cars that you're going to get in the future are based on this.
This slide is are you saying that basically middleware, and then you collect all the information, even though some of the sources are not necessarily accurate. You just kind of grab information here, grab information there, put together, make some sense, but not necessarily. Yeah.
So why we use machine learning is because we have imperfect data set. The reality is imperfect, right? I can't get an image of every single possible car that's in existence. Right. I can get images of a lot of cars, but people do custom hot rods. Right. People do make the Batmobile, and the Batmobile doesn't look like any other car. Right? So machine learning, you say okay, I'm going to take a fuzzy approach to this. I'm going to say, okay, does it have 4 wheels? Does it have, are there seats involved? Does it have glass mirror? stuff like that. And you approximate, yeah, it's probably a car. But it's never, and there's all sorts of examples of where machine learning gets stuff wrong. It misclassifies an animal or something like that. And there's a field of machine learning called adversarial machine learning, where you're trying to predict, as an attacker, you're attacking the machine learning algorithm. And you're trying to predict what you can send to it to cause it to predict wrong and land in that 2% or 1% error place that they have. So, and that's a whole other field of adversarial machine learning. But yeah, so what I did is I take more of a mentality of, I'm not going to have perfect data sets. Even if I go to the system admin, he may not have kept his list up to date. So there's going to be there may be some bad entries. Or I'm going to have gaps in the knowledge because there's an acquisition that just occurred and they haven't been incorporated into the corporate flow yet, all those sort of things. And so, in a lot of the research I do, I have sort of a Borg-like mentality. If you don't know the Borg, it comes from Star Trek. And they're an alien race that assimilates every culture that they encounter into their own. And they don't care if it's a primitive culture or an advanced culture. They just assume either way there's going to be something of value that they can steal from that culture, and they assimilate it in. And then they take the good parts, they throw out the bad parts, and then the Borg is a bigger collective because of it. And so what I do in a lot of my research is I have sort of a Borg-like mentality. I will go take data from anywhere I can find it, and then I will deal with the imperfections and do the tuning to handle the errors at a later stage. And so one of the projects I created was a project called Marinus. And it was based on this idea where I wanted to play with graphs, and I wanted to get a picture of Adobe's externally facing infrastructure. Adobe's very much like the images I showed at the beginning, where we have a lot of endpoints out there on the internet, and it's very complex. And what I wanted to be able to do is I wanted to be able to scan at scale. Adobe has 60 to 80,000 web servers running on the internet. And you want to be able to scan those at scale. But to scan them at scale, that presumes I know what the 60 to 80,000 web servers are. And I did not know that. There was no one place at Adobe I could go and find that information. But I wanted to generate this automatically too. I didn't want to send emails and have people send me Excel spreadsheets back. And this idea is not unique to just my project. There are similar projects like OWASP, MAS, and another project came out recently called Spiderfoot, which also reflects the techniques I'm going to show you. And so what I did is I pulled from internal data sources, the ones I did have access to and I could get fairly easily, because why not? But I actually considered them to be more likely to be untrusted, because they were more likely to be that incomplete network diagram, or maybe the data wasn't up to date because we hadn't done the house cleaning as soon as we did. Instead, I basically went to Google and said, hey Google, what do you know about our network? And so I pulled from security sources, VirusTotal, certificate transparency logs. Rapid7 has an open data project where they scan the internet. But I also looked at non-security sources. So when you do research and development, the very first question you have to ask yourself is, has somebody else already solved this problem? And it can be easy to just think about what security people have solved this problem. But also you need to ask whether developers have solved this problem. Don't just confine yourself to think about security. So Common Crawl is an open source search engine. I used Google DNS. I found out MAS came out shortly before I open sourced my project. I've been working on mine for 4 years. It just took me a while to open source it. And they came out first, and rather than me trying to compete with what their tool did, I just incorporated their tool into my own. I said, fine, I'll support their sources. And they pull from security sources like I do, but they also pull from non-security sources like the UK Government Web Archive and others, and Bing and other search engines as well. There's a lot of data out there. It may not all be in the security space, but it may already be out there. And so you always want to think about whether people have solved this first. And then there's a JavaScript library called D3GS, which is really good for creating graphs. Those initial Death Star pictures I was showing before, I don't know that they were made with D3GS, but they likely were. And so I started to create this network map. And you can't read the domain names, and that's not important. But it gave me a map of, okay, this was the primary domain, the top level domain. All these other red boxes here were host names, and those host names led to IP addresses. And I had a feeling of what was going on. I could identify third-party services because there would be DNSC name pointers to the third parties that we used as the underlying technology. If it had a lot of IP addresses associated with it, chances are it was a high traffic source. I could figure out who the cloud providers were as well because I could see where those were pointing off. So like all these green boxes here, those are all AWS. And it gave me a picture of what was going on. And I could do this for any domain at Adobe, and I didn't have to talk to anybody. A lot of people go into computer science because they're not people persons. They don't want to talk to anybody else. I didn't have to talk to anybody to create this. I just went out to the internet, I found everything I needed and put it together. Yes?
You didn't trigger any security alarms within your own company?
No, because I wasn't, I didn't trigger any security alarms with my own company because I mostly did not scan my own company. There are a couple of exceptions to that if you look at the tool, but even then I'm not scanning, I say hello to the home page and I get the headers back from it, so I can get an idea of the headers. But I'm getting the information from open sources. I'm going to certificate transparency logs that are run by the certificate issuers, or I'm going to the UK government. If I'm using a MAS, I'm looking at the UK government. So I didn't even have to. I didn't start actually scanning the network myself until later with the tool. So yeah, I could do this without sending a single ping to my company. You do have to be careful that you're not abusing the people that you're getting the data from, and throttle your connections and all that sort of stuff. Yeah. So you're not DOSing them, trying to pull down all this information. But yeah, no, I didn't have to talk to anybody at Adobe, which was a bonus for me. Because if you're dealing with those companies with the 2 pizza box rule, that's a lot of people to talk to.
Yeah.
And a MAS does very similar stuff. They throw their data into Maltego. You may have heard Maltego in some of the other talks. And it allows you to graph out what a network looks like. And this can give you information about, sometimes when you're doing a pen test, you don't want to test the third party that they happen to be leveraging underneath. So knowing that the domain name points off to a third party is useful because you're not going to get paid for hacking the third party, or you may trip a legal boundary by hacking the third party. You want to make sure that you're hacking stuff that you own, or in this case, they're pointing to rack space for it. So a MAS is actually a better tool if you like to do bug bounty stuff because they're a little bit more geared towards penetration testers. My tool is geared more towards large companies that have to solve this problem. But it had some drawbacks. So I can't identify who the owners of the machines were, right? If I go and I find a problem with one of these instances, I don't know where in the company I have to go to find it. It didn't explain the conceptual relationships between the endpoints, and I couldn't actually walk the graph with code. Right? This created a picture, and pictures are nice, but I don't want to look at 200 pictures of services. I want to be able to go through this data programmatically, so I don't have to stare at 200 individual services. And if you're a reverse engineer, I was kind of looking for what IDAPRO is for microservices. IDAPRO is a very popular reverse engineering tool today. NSA this last year released Girdra, which is a new hotness. But these tools all give you a function flow of how data goes from one place to another. And this was also one of the things that I wanted to be able to solve because with 200 microservices, with all these different microservices, I had no idea how the flow between them worked. And I wanted to be able to produce this type of flow, which I used to be able to get from tools when my binary days I could get from a tool like IDA. So I first went and tried, like I said, if you're a good researcher, you will go out and see who solved this first, and you'll look at developer tools. So there's a third-party service called New Relic. It's fairly popular. It allows software developers to manage what they manage their software stacks and look for spikes in load and other things associated with the code. And you have to, for a lot of things, you have to include it into the build of the code. So if you're doing Node.js, there's a library that you would include into the server, and that allows it to monitor what's going on in the server and help you figure out where you've got performance bottlenecks and stuff like that. But it also would give you a map of what the services talk to, which was close to what I was going for. And but the problem is that because it has to be compiled into the code, not everybody uses it. Even the people who do use it don't always use it consistently. They sometimes just deploy it on the stuff that they care about monitoring. So I could use this as, in my assimilation approach, I could use this as something I could pull data from as a source of information, but it was not going to be perfect because it would only solve it for places that use this. There's another open source tool called Cloud Mapper, which was created by Duo Labs, where they try to put together maps of how things relate in a cloud environment. And this was good. It's a pretty cool tool, but it worked primarily for AWS. And like I said, I have to deal with Azure and Google Cloud Compute. But they would go and they build graphs, and then you could look at it and try to figure out, like, hey, does that line really need to connect to that line, or should we get rid of that connection? Why is that connection there? And it started as a general purpose tool, and then they started adding security to it.
The cloud mapper, does it allow you to see the whole thing, the hybrid cloud?
No, it's specific. Last time I checked, it was specific to AWS.
Oh.
And what it does is it talks to AWS APIs to get the information about what the firewall rules are for each of the services, and what services have permissions to talk to other permissions based on the authentication rules. And it doesn't have a true cloud backend. Some of the tools I showed you do use like Neo4j, which is a database in the cloud backend, but it doesn't have a true graph backend, graph database backend. It does this through libraries and code. And I know, being an engineer, of course, you always want to build it yourself. It's something you have to break yourself of. But what I want to be able to do is I want to be able to build a real graph. And so Gremlin is a language. It's the language that is used by most graph databases. There are other languages for graph databases like Cypher. Cypher is specific to a graph database known as Neo4j, but even Neo4j supports Gremlin. So when I started to dig into graph databases, and if you look at graph databases, it's a really complex market, depending on a whole lot of factors. It's as an industry, it's in the phase where the initial ones prove their values, and then now there's 20 vendors in the market. They haven't distilled down to a handful of key winners. So they're still at the phase where there's a lot of them out there, and I don't have time to go into the differences between all of them. If you ever want to play with one, Apache Tinkerpop's an easy one to set up. Neo4j has a freeware version of it. Ones like Janus Graph are more interfaces to other data stores. So Janus Graph can sit in front of Elasticsearch and Hadoop and help you generate graphs based on the data that you already have stored in those data stores. So that's what sort of makes it complicated. Some of them assume that you have existing data stores and you just need to be able to build a graph out of that data. Others will provide the data itself. So I'm going to give you a really quick primer on graph databases. If you've taken algorithms and their analysis or some sort of class to that effect, and you had to study things like Dijkstra's algorithm in your computer science courses, this will all make sense to you. If not, it may be new. But basically with graphs, you have vertices and edges. You have points and you have lines that connect the points. And in a graph database, one of the reasons that people like them isn't just because that they allow you to connect data and show the interrelationships between data, but the performance is based on the distance you have to travel when you do your query. So how far are you actually going to walk in the graph? That's what primarily dictates the performance. It's not based on how much data you have in total. So if you're familiar with SQL databases and you're doing table joins, every row in this table has to match with every row in that table, and they got to do huge merges, and that's kind of a big performance thing, regardless of how many of the rows you're actually going to get returned. With a graph database, it's more about just once you find the spot you're starting from, it's just how far you walk from there. And what makes them useful in my scenarios is that, one, a universally identified identifier between data sources is not required. So, as I said, I go out and I take a Borg-like mentality. I'm pulling from all these different data sources. And they don't have a nice, convenient primary key that they all share to represent what it is that they're looking at. Sometimes it's a GitHub URL, sometimes it's a service name, it might be an entry in Jira, which in a SQL database would make it hard to map up because I would need keys to be able to do all these mappings. But with a graph database, it doesn't matter why the two pieces of data are related. You can just say that they are, and that's good enough. And you can query the graph without having any knowledge about why they relate at the beginning of the question. So, I can ask a very simple question like, does Bob know Steve? And it doesn't matter how Bob knows Steve. They could be cousins, they could be coworkers, they could be apartment mates. It doesn't really matter. I can just ask the question in general, does Bob know Steve? And that makes things a little bit easier. And that also doesn't matter how, it can also handle the recursion. So, if I say, does Bob report to Steve? It doesn't matter if Bob's the immediate manager or Bob's manager of Steve, or Bob's the CEO and Steve's at the tech desk. It'll handle the recursion of that as well. So it allows you to ask these really generalized queries about how things connect. Vertices are like classes. They have a label which gives them a type. So like when you do Java programming, you can have a class that represents animal, you can have a class that represents plants. With vertices, you can have a vertice that represents an animal, you can have a vertice that represents a plant. And then you can have properties associated with it. Similar to how in a class, classes also have properties. Unlike classes, you can't assign method functions to them. Edges also have labels, so you can label why two things are connected. You can say, is this person's cousin? Is this person's manager? Is this person's roommate? They can have an optional weight that's sometimes important depending on types of graph queries you're doing, so that when you're doing a query, it will avoid paths that have a higher weight and maybe go with ones that have a lower weight. So like if you're doing a graph of a city, freeways might have a lower weight than city streets because your mapping function wants to encourage the use of freeways over stop-and-go city streets. And as I said, they can handle the recursion and be generic. There are a couple of cautions when using a graph. Because the edges are directional, sometimes you want to do a bidirectional connection, sometimes you don't. If you make everything a bidirectional flow, you can create loops, which creates issues. If you start to see a lot of vertices having the same type of property, you should maybe consider making the property its own vertice. And they can sometimes be tricky to rebuild because you lose track of where you found the information. But the advantages are that because the information is more loosely tied, I can incorporate more data from more tools into the graph. I don't have to know how the things are going to relate all in advance. I can just start throwing things in there as vertices and edges, and then figure out what it looks like at the very end. And I think I've already covered some of these other points, so I'll just go ahead and skip ahead. So I started another project which I called Abacus. And what I wanted to be able to do is, I wanted to be able to solve ownership problems within Adobe. So if I find an issue in a piece of code, or I find an issue with a particular domain, I want to be able to figure out who owns that. Because finding vulnerabilities is great, but since I work as a defender, I then have to go figure out who to give that to make sure it gets remediated. I wanted to be able to have a single pane of glass for information. When you go into the field, the idea of a single pane of glass gets brought up, and what that refers to is you'll have like 12 different tools. You'll have a static analysis tool, you have a web app pen testing tool, you'll have a threat modeling tool. If you want to figure out the security of something, you have to go log into each one of those different interfaces. And each one has its own authentication, and the data is represented differently, and you'd rather have just one place to go for that. And that's usually what people refer to as a single pane of glass. I want to be able to contextualize something. If I find a vulnerability in a piece of source code, is it exposed on the internet, on hosts? How many hosts is it actually exposed on? Maybe I want to kick off a scan of that host. So I want to be able to contextualize, like, hey, I found this vulnerability. Is it an actual risk, or is it just more of a hypothetical lab environment vulnerability? As I said earlier, I want to express the relationship between the hosts, and I want to be able to attack at scale. Like I said, we have a whole bunch of different services. They all act differently. And I wanted to be able to scan all of them intelligently without having to know the context of each one. And so this is part of the reason why I had to do this in code rather than just on paper or on my laptop. And I can make more intelligent decisions, right? So which services have the highest vulnerability accounts based on all the different tools that I'm pulling from? Our static analysis tools, our third-party library tracking tools. I can go and I can look at all these things and I can say, okay, which of these have the highest risk? And then I can go kick scans off on them to prove that they're actually high risk or to quantify the risk. Because sometimes static analysis findings have a bunch of false positives, and that makes it hard to know whether it is. If I have all the projects in there, I also know which ones are not tracked by the different security tools. and I want to be able to identify the sensitive flows. So I started pulling this information together. The main thing you have to take from here is I'm starting to get all this information to a single pane. I start with a service name, and I say, tell me everything you need that there is to know about this, and it starts coming back with where it is in GitHub and the stack analysis from check marks and the third-party libraries it's linking and how many vulnerabilities there are in that. And then from there, I'm able to actually create the graphs. Now you'll notice that all these graph connections are bidirectional. I took this before I figured out the problems with bidirectional data flows. But you can see here I can go from an AWS account. I can link through a couple of different things, and I can eventually get down to a GitHub location and security. And this is important because now I can say, hey, I found this vulnerability. Where in AWS is it deployed, and can I go attack that? Now I can do intelligent attacks because I've got something here which is a probable attack. Maybe there's a named vulnerability on the internet. Maybe there's a new CVE that's come out that affects a lot of software, and I can go through all of GitHub. I can figure out that CVEs, which source code has a library that has the CVE, and then I can start tracking that back to where it's deployed, and I can go directly to testing that. And I can do this in a generalized way without having to know the teams, and I don't even care what the application is. To me, it's just a source code finding an IP address. I don't even have to care what the application is. And then also I can map things back for getting the information back to the developers. Because again, finding a vulnerability is great, but if you can't do anything with it, then you're stuck, right? You have to be able to find which of the 2 pizza development teams in the company is actually responsible for this code, so that you can get it back and get remediated.
And how do you know who's the owner of that asset? Is it within Jira? You're pulling that information?
There's a couple of places. So, and it depends on the individual team. So I could get it from Jira, and I could try to infer based on who's filed bugs. I could try to infer it based on who's committed to that code in GitHub. Again, Adobe's a big place. Not everybody uses GitHub. We also use Perforce. I can infer it that way. There are other. I can go look at the tools and figure out who's been uploading the tools into our. Who's been uploading the code into our security analysis tools, and say, well, okay, if they're actually pushing it into the security analysis tools, chances are they're on the team, and chances are they actually care about security. So maybe that's the person to go after. So there's a couple different ways that I can go and figure this out. The type of contacts I have will vary. Sometimes I have business level contacts. Sometimes I have engineering level contacts. It depends on the source of the tool. But even if I'm off by a little bit, if I hit the business level one, I meant to get an engineering level one, I'm still in the right area, right? Adobe's a globally distributed company, so like just even getting to the right office is sometimes a start. So to go ahead and wrap up, when you get out into the real world and start working with companies, you're going to deal with imperfect data. You're going to deal with imperfect situations, the countertop that's not level, the door that doesn't have a square frame. And so you need to find ways of thinking about problems to solve that. And one of the things that you want to make sure you do is you don't want to get in the mindset of, if it's not perfect, it's not worth starting. Or if I can't get a 100% answer, it's not actually worth doing. Sometimes if I can only get a 60% answer, that's still better than a 0% answer. It means that we're actually doing something where we can, and I can figure out how to solve the other 40% at a later time. And graphs are a really good way of thinking about problems. I've shown where they were used in other spaces, either for incident response. Maltego's used heavily in incident response, or Cloud Mapper, or the Insanity Bits tool, where you looked at how processes relate to each other, or spam. They not only help you visualize things, which are good for understanding things when you're specifically looking at the problem and you're digging deep into it, but they're also good in a much general place where I'm trying to do everything in code, and I don't want to know the details of everything in advance. They're also really good at creating an abstracted view that code can then go and log. So I can go and I can take that GitHub location. I can say, for every place in GitHub you find the problem with that CVE, go find its associated IP address, and then kick off one of our testing tools to go verify whether that's an issue. And that can help me t-shirt size a problem. So when there are named vulnerabilities on the internet, like shell shock or and those types of situations, you have to react very quickly, right? Like a new vulnerability, a new 0 days just dropped. You have to be able to immediately t-shirt size how big of a threat is this. So you need to be able to go and quickly figure out who within the company has this, where is it deployed, is it internet accessible, and maybe do a couple of initial scans to be able to say like, oh, this is going to be a really big thing for us. We're using this everywhere, and it's easy. All of our tools are able to trigger it from the internet, or be able to say like, and it's used by 2 teams on less critical infrastructure. When 0 days drop, you have to be able to do that kind of critical analysis fairly quickly. And so that's by building the graph and building these relations. Even using imperfect data, I'm able to answer those types of questions. And also, graphs help you think about ways in the way the attacker sees it, right? Every day we're getting scanned by hackers who are just crawling the internet. They're just going IP by IP, scanning, looking for vulnerabilities. So they don't even care what your company is. They're hunting that way, and they're just graphing the entire internet. So you need to know what your network maps look like, because the attackers already do. There's entire data sets, like the Rapid7 Open Data Project, which I mentioned. They start at 1.1.1 and they scan all the way through to 255. And then they post all that information online and make it freely downloadable. So you want to be sure like you're taking advantage of that information, because the attackers definitely are. And if you can put it together in a graph, then you can actually get a picture of what's actually deployed and what you have out there. And like when I did the Marinus project, I found stuff even within my own team, which is the security team, that was exposed that wasn't intended to be exposed. All of our threat models that are designed and our shift left philosophy said, oh yeah, it's not going to be exposed. We thought about that at the beginning of the project. And then it turned out in reality it was, and we were able to catch that. So when you're thinking about problems, think about things in graphs. Think about graph data sources. Think about how you can assimilate data and make relationships to do things at a very large scale. With that, I think I'm at time, so I'm going to go ahead and wrap up. Are there any questions? That's my contact info if you want to reach me.
I guess if you're just getting started
Mhm.
mapping, like say, infrastructure as crazy as AWS,
Mhm.
Google Cloud, and like Azure at the same time, what would you recommend to get started?
The best way, everybody has their own way of learning, and it depends on how your mind works. I typically go, the way that I started is I just went and I tried deploying a couple of things. Just like go set up a free account and try to set stuff up, use the interfaces. Amazon's hard because they have acronyms for everything, and they've been around for a long time, so they've got tons of them, and it's hard to figure out what they all mean and all that sort of stuff. There's a lot of information that's available online. Typically what I do is I will go and I'll futz around on the site, kind of poking here and there until I find something that grabs my interest, that I would actually care about or might seem interesting to me. And then I start going and grabbing the YouTube videos for that, and I kind of explore from there, because if I start with the thing that has an interest in me, at least when I'm watching the videos, I care more about it, versus like just going and watching like general videos and having word salad thrown at me, and having it like, okay, I still don't know anything more than I did when I started. I just have a lot more terms in my head. I'm a learn by doing kind of person, but so that's how I approach it. But other people have other techniques. There's definitely a wealth of information out there. The problem is trying to find the hook where you need. And so sometimes finding that hook is finding a problem that's interesting to you, and then trying to figure out how you would use their solutions to solve that problem. And then that forces you to actually think about the services in a real tangential way, rather than just like an academic way of, here's a bunch of terms to memorize. Please memorize them for tomorrow's quiz. I usually go and I try to figure out, it could be a really simple problem, just enough to like start the process and go. Or you can go to user groups, like find the local user group and just attend the meetings and hear people talk about them and talk to people about them. And then the information is associated with people that you've talked to, and that sometimes helps. Any other questions? All right, well, thank you for your time.